Hey, welcome. Today, we're going to dive into a pretty wild, hidden force in engineering. It's this invisible frequency that's so powerful it can make massive, high-speed machines literally tear themselves to pieces.
So let's just start with this question. Have you ever thought about what makes a perfectly good machine, something spinning incredibly fast, suddenly start vibrating like crazy and then just completely fail? Well, it's not random, and the answer is actually fascinating.
All right, so this whole thing really boils down to a high-speed problem. You see, as we build machines to spin faster and faster, we're talking jet engines, power turbines, you name it, they run into this really dangerous, invisible enemy, vibration, that just gets out of control. And let me be clear, we're not just talking about a little rattle or some weird noise. At these kinds of speeds, vibration creates forces so intense they can lead to total mechanical failure. We're talking millions of dollars in damage and, a huge safety risk.
Now, this kind of disaster-level vibration doesn't just happen at any old speed. Nope, it happens at a very, very specific point. You can think of it like the machine's kryptonite, and engineers have a name for it, the critical speed.
Okay, so to really get what critical speed is, we've got to talk about a basic law of physics called natural frequency. Everything, and I mean everything, from a guitar string to a giant bridge to a spinning shaft of steel, has a natural frequency. It's the frequency it wants to vibrate at if you just, give it a little tap.
And this is where it gets dangerous. When the speed of that rotating machine perfectly matches the object's natural frequency, boom! The vibrations amplify like crazy. They feed on themselves. That matching point is the critical speed. It's called resonance, and it's when the system basically starts to shake itself to pieces.
Now, here's what makes this so incredibly tricky for engineers. That natural frequency isn't some universal number. It changes depending on what the thing is made of, its shape, its weight. So a shaft made from regular old structural steel, it's going to have a totally different set of critical speeds than one made from a fancy titanium alloy.
So if this critical speed is this invisible, material-specific threat, how in the world do you predict it before it's too late? I mean, how do you see something that's literally invisible?
Well, they do it with a really impressive toolkit of analytical methods. They use stuff like modal analysis, which is kind of like figuring out all the different musical notes a bell can make when you ring it. They use the finite element method, or FIM, to build these super complex computer models that predict behavior. And they use tools like FFT analyzers, which are almost like a doctor's stethoscope for machines to measure vibrations in the real world. And believe me, this analysis is no joke. This isn't some quick, back-of-the-napkin calculation. We're talking about engineers creating and studying these incredibly detailed 2D and 3D digital versions of the parts just to simulate exactly how they're going to act under all that stress.
And get this, they're not just looking for one single critical speed. A single spinning shaft can have tons of different natural frequencies, or modes. In some of these studies, engineers are analyzing the first 12 modes of critical speed for just one part. That is a dozen different speeds they have to know about and design the machine to avoid hitting.
So all of this incredible work, all these complex models, it all leads to one absolutely critical goal: the power of prediction. Because in this game, being able to accurately see these invisible frequencies ahead of time, well, it's everything.
I mean, it's right there in the research, which says accurate prediction of the natural frequency mode is important for preventing damage and vibration during high-speed rotation. It really is the first and most important line of defense.
Think about it. You can't see the vibration building up until it's already too late. You can't just wait and react to it. The only real defense you have against this kind of catastrophic failure is getting the math and the computer models right from the very, very beginning.
But wait, there's another really cool layer to all of this. Predicting that natural frequency isn't just for preventing disaster. It's also an incredibly powerful tool for diagnosing problems. Why? Because a tiny, invisible crack in a shaft will actually change how stiff it is, which in turn changes its natural frequency.
This is how it works like an early warning system. The science shows a hidden flaw is indicated by reduced critical speed. So what does that mean? It means if your machine suddenly starts to vibrate really badly at a lower speed than you predicted, that is a huge red flag that a crack has probably formed somewhere inside.
But here's the catch. That amazing warning sign is completely and totally useless if your original prediction was wrong to begin with, right? If you don't know exactly where the target is supposed to be, you have no way of knowing when it's moved. Accuracy is just as crucial for detection as it is for prevention.
And that really brings us to the ultimate goal here:
The whole reason for all this research, this ongoing quest in engineering, is to keep refining these methods, to keep improving the models, and to just increase our confidence in every single prediction we make. It's all about making sure our high-speed world keeps running safely.
So I'll just leave you with this thought. If being able to predict these invisible forces is so absolutely critical for the health of our machines, where else in our lives, in our economies, in society, in the environment, where else are we failing to see the hidden frequencies just before things start to shake apart?